This is the 14th video in our series on Lie algebras. In the previous video, we looked at Cartan's criteria for the solvability of a Lie algebra. And today we're going to look at Cartan's criteria for the semisimplicity of a Lie algebra. But let's recall a couple of definitions to get off the ground. So we'll say that a Lie algebra L is semisimple if its nil radical is equal to 0. And what do we mean by the radical of L? Well, the radical of L is the maximal solvable ideal of the Lie algebra L. So if the radical is 0, that means that the Lie algebra does not have any solvable ideals. Okay, and then, well, we also need to recall something called the killing form. And so the killing form of a complex Lie algebra, this could be defined over a Lie algebra with an arbitrary field, but we're going to deal with complex Lie algebras today. Okay, so the killing form of a complex Lie algebra L is a bilinear form kappa from L cross L to the complex numbers, defined by kappa of xy is the trace of add x, add y, where of course those are the linear transformations on L as a vector space determined by, well, the adjoint action of x and, well, the adjoint action of L, which has to do with the bracket of x with something else or the bracket of y with something else. So we looked at that in the previous video. Okay, so furthermore, for a vector space or a vector subspace W of L, we can define its orthogonal complement with respect to this bilinear form kappa, or the killing form. So let's say W perp is all elements x from L such that kappa of x with W is 0 for all W in W. So kind of the standard way to define the orthogonal complement. Okay, so let's start with a lemma, and that says that if we have an ideal I, then I perp is also an ideal. Okay, so let's see how we can do this. So let's suppose that we've got x in L, and this is any element of the Lie algebra. And then we'll also suppose that we have j inside of the perpendicular complement of I. And then, well, let's just really quickly recall what it will take in order for this to be an ideal. Well, I guess first it has to be a vector subspace. We won't check that. That's fairly straightforward. That's something you probably did in linear algebra. What we'll check is the absorption property of the ideal. So in other words, what we want to show is that the bracket of x with j is inside of I perp. So that's what it would take for this to be an ideal. Okay, so, well, how do you get inside of the orthogonal complement? Well, you do kappa with ij, or, well, of course it's going to have to do with this definition over here. Okay, so let's do that. So let's take I from the ideal, and this is any I from the ideal, and then observe the following. So let's do kappa of I comma the bracket of x with j. Okay, so just to reiterate, that's equal to 0, or if that were equal to 0, then the bracket of x with j would in fact be an I perp. Okay, so now we're going to use a property of the killing form that we proved in the previous video, and that goes like this. So this is going to be kappa of, let's see, I with x, or the bracket of I with x comma j. So again, that's a really nice property of the killing form, is that you can move this like Lie bracket around inside of it, if you will. Okay, nice. But now let's observe that I itself is an ideal. So that means that this object right here is inside of I. That's by the definition of an ideal. So now let's see what we're doing. We're finding the killing form of something from I with something from I perp. Remember, j was an I perp. But if you do the killing form of those two types of things, well, you definitely get 0. But then that's exactly what we needed to show by our previous discussion. Okay, so let's move on to our main result for the video. Okay, so our big result for the day will be Cartan's criterion for semisimplicity, like we mentioned earlier. So let's suppose that L is a Lie algebra over C, in other words, a complex Lie algebra. Then the result says that L is semisimple if and only if kappa, the killing form, is non-degenerate. What do we mean by non-degenerate? Well, we mean that if x is a non-zero vector, then kappa of x with itself is also non-zero. Now, you might remember from linear algebra that this is something that generally applies all of the time, but that's for an inner product, which is a special type of bilinear form. So, bilinear forms may have degeneracy in them, if they're arbitrary bilinear forms, that is. Okay, so let's do this forward direction first. So, in other words, we need to suppose that L is semi-simple. Keeping in mind that it being semi-simple means, well, that rad L is 0. In other words, there are no solvable ideals. Okay, so now let's notice that L is an ideal of itself. So I'll just write it like this, but we want to think about L as an ideal over itself. But then, well, what does that tell us? Well, that tells us that L perp is also an ideal. So is an ideal as well. And that's by the last lemma. Okay, great. And so now what we want to do is take two elements from L perp, or actually three elements from L perp. So x, y, and z inside of, well, I would say the orthogonal complement, but it's really the killing form complement of L. Okay, well, now let's observe the following. Notice that the bracket of x with y is going to be in the derived subalgebra of L perp, just by the definition of the derived subalgebra. So that's going to be L perp prime. Okay, so now let's do kind of the final calculation for this direction. So maybe I'll just put here that we're going to notice the following. Let's do kappa of the bracket of x with y with z. But now, well, what do we know about that? Well, we know that that in fact has to be equal to 0. And how do we know that that's equal to 0? Well, observe that the bracket of x with y is most definitely inside of L. I think that's pretty clear because everything is inside of L, including L perp, which is kind of a strange thing to think about. And then z is inside of L perp. Okay, but then this being 0 actually implies that L perp is solvable. And that's by Cartan's criterion for solvability from the last video. Okay, but then if L perp is solvable and it's an ideal of a semi-simple Lie algebra, what that tells us is that, well, it tells us that L perp is in fact equal to 0. Okay, but if L perp is equal to 0, well, notice by the definition of this complement of L under the killing form, that means that our kappa is non-degenerate. Okay, good. Okay, so good. We've got this forward direction. Now let's look at the reverse direction. Okay, so now for the reverse direction, we're going to be using the contrapositive. So let's suppose that L is not semi-simple. Okay, so if it is not semi-simple, then, well, what does that mean? Well, that means it has solvable ideals. So it has solvable ideals. Because, well, it not being semi-simple means, well, the radical is not 0. And if the radical is not 0, well, it in fact at least has one solvable ideal, the radical itself. And I guess I should say it has non-trivial solvable ideals, but I think that kind of goes without saying based on what we've said out loud. Okay, so let's take one of these solvable ideals. So let's take I, and I'll just make sure and say that this is non-zero. So we've got a non-zero solvable ideal. But what does that tell us? Well, that tells us that there exists some natural number n such that, well, in is equal to 0, but I upper n minus 1 is non-zero. Just recall the definition of solvability had to do with this string of ideals that we built by bracketing ideals with themselves. But now let's observe something that happens for all solvable ideals, or really for all solvable Lie algebras, and that is the last one of these is an abelian ideal. So let's note that here. So notice that if we set A equal to in minus 1, it is an abelian ideal. Well, why is that? Well, that's because we know the bracket of A with itself. Well, first of all, that's A prime, but that's also equal to L upper n, which is equal to 0, just based off of how we make this string of ideals. And that shouldn't be L upper n, that should be I upper n. Okay, so next up what we'll do is take a non-zero element, little a from A, and then any non-zero x from L. And then, well, let's observe the following. So that for all y in L, the following calculation holds. So we have the adjoint action of A composed with the adjoint action of x composed with the adjoint action of A applied to y is equal to the following maybe object of all of these composed brackets. So on the out, we have the bracket of A, and then we have the bracket of X, and then the bracket of A, finally with Y. So that's just what all of these linear transformations mean. But let's see what we've got going on here. So first of all, we know that A is an ideal. So since A is an ideal, if we bracket A with anything from the Lie algebra, we get inside of A. So that means that inner bracket is inside of A. But then we can just work ourselves out. So now we're bracketing X with something from A. So that means that's going to be inside of A. Oh, but now we're bracketing A with something from A. So that's in fact inside of the bracket of A with itself, which is, equal to 0 as we saw before. So, well, what does that mean? That means the following. If we take add A, add X, and we square it, we get the 0 map. Well, and how do we know we get the 0 map? Well, because whenever we do add X, add A, add X squared, we're going to end up with something like this. It's just this Y is going to be replaced with, let's see, the bracket of X with, well, whatever we're plugging into this map. Okay, so, well, what does this tell us? Well, if a linear transformation squares to 0, that means it's nilpotent. That's the definition of nilpotent, or it doesn't have to square to 0. It has to, somehow have a power that's equal to 0. So that means add A, add X is nilpotent. But what does that get us? Well, recall that the trace of any nilpotent linear transformation is 0. So this means that the trace of add A with add X is, in fact, equal to 0. Oh, but look what we've got right there. The trace of add A, add X is, in fact, equal to kappa of A with X. But now, notice that this holds for any non-zero A in A and any X inside of L. Well, we might as well set X equal to A, and what we'll see is that kappa of A with itself is 0. But that's exactly what we needed for this killing form to be degenerate. proving this reverse direction by the contrapositive. Okay, so for our next result, we're going to prove, well, essentially why this definition semisimple has the word simple in it. Okay, so for our next result, we'll tie together the ideas of a simple Lie algebra and a semisimple Lie algebra. So let's recall that a Lie algebra is simple if it has no non-trivial ideal, whereas it's semisimple if it has no non-trivial solvable ideals. So how can we bind these two together? Well, via the following result. So let's suppose that we've got a Lie algebra over C, so a complex Lie algebra. Then L is semisimple if and only if there are simple ideals L1 up to Ln, such that L can be written as the direct sum of L1 plus L2 all the way up to Ln. Okay. So this is an if and only if statement. Let's do this forward direction first. Okay, so and how are we going to do this? Well, let's do this by induction on the dimension of L. Okay, so, well, if we're doing it by induction, well, we obviously need a base case. So the base case will be the dimension of L is 1. But any one-dimensional Lie algebra is simple. I think that's pretty evident. So here we've got L is simple itself. But if it's simple itself, well, it's clearly written as really the easiest version of a direct sum of simple ideals. Okay, so now let's look at our induction hypothesis, which will lead to the induction step. Okay, so let's suppose for all Lie algebras of dimension less than m, the statement holds, and that the dimension of L is equal to m. So we're using a strong induction hypothesis here. Okay, so now let's let I be an ideal of L. So let's let I, which is a non-zero ideal, so let's write that, be an ideal of L of minimal dimension. Okay, so we look at all of the ideals of L and we pick the one, or we pick one of the ones that has the smallest possible dimension. So this actually breaks into two cases, because we could have the case where the smallest dimensional ideal we could get would be the dimension of the Lie algebra. Well, in that case, the ideal is equal to the Lie algebra. So we have I is equal to L. But if the smallest ideal we have inside of L is the Lie algebra itself, well, then that means that L is simple. And then we're done for the same reason we were done in the induction hypothesis. Okay, so otherwise, so in other words, if I is not equal to L, then we write the following. So we can write L as I direct sum with this I perp, this complement of I under the killing form. And now this is not totally evident by the definition of the killing form, but it in fact follows from the fact that we can show that I and thus I perp are both semi-simple. And well, let's maybe explore how we know, not that they're semi-simple, but how we know that we get a direct sum here after showing that they are semi-simple. So notice that I intersected with I perp is equal to 0, and that's because of the following. So that's because I intersected with I perp is a semi-simple ideal. That's really because any ideal of a semi-simple Lie algebra is semi-simple. Again, that's going to be something that we show just coming up. But if X is in I intersect I perp, then that means that kappa of X with X is equal to 0. just consider the x from the first entry to be an I and the x from the second entry to be an I perp. But then by definition of that complement, you get 0 there. But that means that either kappa is degenerate or x is equal to 0, but that means that x is equal to 0 because we know that kappa is non-degenerate because of our last theorem. But that means that I intersected with I perp must be equal to 0. But, well, that tells us that when we take this sum, we in fact get a direct sum. Okay, and then, well, the next claim that we'll have is that I and I perp, really any ideal of a semisimple Lie algebra is semisimple. So let's get to that. Okay, so let's recall that we took I to be a non-zero ideal of L that was of minimal dimension. Now we'll show that I, that ideal, and, well, its orthogonal complement are both semisimple. Okay, so let's suppose that we have a ideal J of I, and it is solvable. So let's say is a solvable ideal. Okay, nice. But then the bracket of J with I perp is contained in the bracket of I with I perp, but then that's equal to 0. And I guess maybe this is a little bit of a homework exercise, that elements from I commute with elements from I perp. So like I said, I think that's a nice homework exercise. But what does that tell us? That tells us that J is a solvable ideal of I perp. Okay, but then if it's a solvable ideal of I and I perp, then that means that J is a solvable ideal of I plus I perp, which is equal to L. But then, of course, that is a contradiction. Okay, great. And then finally, we're ready to finish off this direction. So let's take L, and like we did before, we're going to write it as the direct sum of I with I perp. But now recall that I had minimal dimension, but that means that I itself is a simple ideal. How do we know that? Well, if it's not a simple ideal, it has an ideal of itself, which is lower dimension, but then that's going to be an ideal of the whole Lie algebra with smaller dimension, contradicting the minimality. So that means, well, we can just rename this I real quick as L1, which, you know, like we just discussed, is simple. And then after that, we'll apply the induction hypothesis to I perp. And we know we can do that because the dimension of I perp is strictly less than the dimension of L, and we made that induction hypothesis. But now, well, like I said, L1 was simple, and then L2 through Ln are going to be simple by the induction hypothesis, meaning that we have decomposed L into a direct sum of simple ideals as needed. Now let's look at this reverse direction. Okay, so now for the reverse direction, let's suppose that we can break L as this direct sum of L1 to Ln, where these Lk are simple ideals of L. Okay, but now what we need to show is that L is semisimple. So what we'll do is take the radical of L, the largest solvable ideal. Okay, so let's let I equal rad L, like I just said. And then next up, let's set I sub k equal to the bracket of I with L sub k. So we can most definitely do that. That's just the bracket of two ideals, which is a new ideal. That's something that we showed a long time ago. And then furthermore, let's note that I sub k is, well, it's going to be a solvable ideal of L sub k. So there, we've got that. It's a solvable ideal. But then, well, recall that L sub k was simple by our original assumption. So that means it doesn't have any non-zero ideals, not to mention, non-zero solvable ideals. So this means that I sub k is equal to 0. And this is going to hold for all k between 1 and n. Okay, so now, well, let's see where we can go from there. So now let's do the bracket of I with L and see what happens. So this is going to be the bracket of I with L1 plus all the way up to Ln. But now notice that's going to be the bracket of I with L1, the bracket of I with L2, all the way up to the bracket of I with Ln. But we defined those to be I1 plus all the way up to In. Okay, but then each of those was equal to 0 by the line that just happened right above. So we have all of this is equal to 0. Okay, but if the bracket of I with L is equal to 0, well, what does that mean? That means that I lies inside of the center of the entire Lie algebra. But notice that the center of the entire Lie algebra is going to be inside of the center of the direct sum of all of these centers of L1 up to Ln. But then each of those centers is equal to 0 as well because each of the L's are simple. So this is equal to 0. But now we've got I is equal to 0. Remember that I was the radical of L. So if the radical of L is equal to 0, that means L is semi-simple. And that's exactly what we needed to show. Okay, so I've got one homework exercise based on the killing form for you. So here's a nice computational exercise based on the killing form. So let's suppose, or let's show that for all xy in SLNC, kappa of xy is 2n times the trace of x times y. So what's nice here is this is a formula in the end that doesn't have to do with add x or add y, which those are hard to work with computationally. And then the next one is for all xy in SP2n, we have kappa of xy is 2 times n plus 1 times the trace of x times y. You might say, well, what's SP2n? Well, it's a symplectic Lie algebra defined as follows. So it'll be a subalgebra of GL2n, so defined by j times x plus x transpose times j equals 0, where j is this matrix here. So observe that we have 0, the n-dimensional identity matrix, minus the n-dimensional identity matrix, and then another n by n matrix of all zeros. I should point out that these are n by n matrices of all zeros, and that's a good place to stop.